Okay, welcome everyone. This is the week 6 webinar for our online statistics class. And so there's a couple things important about week 6. What's one of them? What's important about week 6? Yeah, it's an even week. 6 is an even number, so that means there is an exam this week. So make sure, you get ready for it and make it happen. In fact, one of the reasons why the project was due last week is that was an odd week, and I don't want to put an exam and the project on the same week. That'd be kind of tough, possibly. So week 6 is exam week. Also, it's a 12-week course, so we're halfway through. So we're moving forward. Not at the beginning, not at the end anymore. So let me tell you about the plan for today. And the idea is I'll always answer any questions you have. You can pop in the chat box, let's say it, whatever, and I'll answer any questions you might have. And then we're going to go and talk about confidence intervals. Turns out confidence intervals is a major application. So pretty much the rest of this entire course is applications. But the hard part is knowing how to do an application. So we're going to be looking at two kinds of confidence intervals today. The first kind of confidence interval will be a confidence interval for a population mean. So the idea is you do a survey and you get your sample mean, but the problem is your sample mean is probably not the same as the population mean. We know from last week that it's the best estimate for the population mean, but more importantly, is it a good estimate? Is it far off, or is it like really close to the population mean, or at least likely to be? And that's what this confidence interval for the population mean will be about. Is it doesn't just tell you what the sample mean is, but it says that it's very likely that the population mean will be between these two numbers. And that's what the confidence interval for the population mean is all about. And then we'll talk about confidence intervals for population proportion. Okay, so we're looking at the same idea, except instead of a quantitative variable, which is what means are all about, we're going to be looking at the yes/no question. And based on that, we'll have a confidence interval for the proportion. Any questions on that idea? And then something that is very important and kind of easy to just like not worry about, but it's really, really important. And that is if you want to conduct a survey and you want to find something out, one thing you might say is, well, how big a sample size do you need so that you can be pretty accurate, right? We found that you needed to be over 30 to have a normal distribution, but that's not the same thing as being really accurate, okay? So for example, if I asked a group of people how tall they were, and I looked at that and I found out that, based on my sample, I can say that, the average adult in America is between 2 feet and 9 feet. Have I learned anything? What do you think? If I can say that the average American, I'm very confident, is between 2 feet tall and 9 feet tall. You think I learned anything? What do y'all think if I said that? Yeah, it's too general, it's too wide. Do you see? It's way widespread. If you want to find the average American, between 2 feet and 9 feet doesn't tell you anything new that you already know. Does that make sense? So you might say, well, we need a bigger sample size to get that margin of error down, or the standard error lower. That standard error is really important. And if to get the standard error small, that's how you can get more accuracy. Because the standard error is small, then you can say you're really close. Your sample mean is likely to be very close to the population mean. So if you could be within like a half an inch, that might give you a lot better information. Does that make sense? So the question is, how big a sample size do you need so that you can get that standard error small enough so that you really do have good estimates? And we'll do the same thing for proportion instead of means. For project 2, we're going to stick with more than 30. We're going to stick with more than 30. And as you mentioned, it could be really rough if you really want a really good confidence interval. Then you're going to say, well, more than 30 wasn't enough. I did 31, but I really needed hundreds. But something you will be doing in project 2, which I'm not quite ready to completely talk about, I'll talk about a little bit now. And that is that you're going to say, you need more than 30 because to do anything, you need that to be able to get any kind of numbers because you got to have a normal distribution. But then another thing you might say is, well, yeah, I need no more than 30, but what if I wanted, if you're doing the heights idea, what if you wanted to be off by no more than a half an inch? Then what I would do is have you calculate how big a sample size you would need. And then remember with project 1, I asked you how you would do future studies. I'm going to ask you the same thing as how do you do future studies? And part of that will be how big a sample size would you need so that you can have better information. Does that make sense? And doing future studies, that is all hypothetical, You're going to have over 30, but I'm not going to make you do a future study next year or something. Any questions on that? But really good question. Really good questions. Okay, so that is the plan for today. Again, this is all about confidence intervals. I will give you a warning, and that is there's going to be a lot of writing. So get used to it. I'm going to give you a lot of templates on words that you need to use, and you need to use those words for the exam, for example. When you're doing the week 6 exam, you're going to have the words, the verbiage that I tell you have to do. So, and I'm telling you that in this webinar. So pay attention to the webinar. Okay. If all you do is, just ignore the whole webinar until I get to the secret word so you can get that secret word quiz, you're going to miss out all of what I tell you have to do for the exam. So it's really important to actually pay attention to the whole webinar. Take good notes and stuff like that. Okay. Any questions? Any questions about anything? Any questions? If not, I have a question for you. I know it's a small group, but here's a question, and here's just a rule about my question. You have to answer the question. If you don't feel comfortable being public about it, then you can lie, but make sure that it is a reasonable lie. So here is the question I have for you. How old were you when you experienced your first passionate kiss? So I want you to put in the chat box how old you were when you experienced your first passionate kiss. And there we go. And 17, we're going to have a huge group, but we got some. Okay. And again, I don't say who's who. All I do is say we got these 4 numbers. Okay. And I will tell you something. I've been doing this since I started teaching statistics a quarter century ago. And I've actually watched it change. Now, with a sample size of 4, there's not much to say. But even that, it looks looks like it should be in terms of recent, where 25 years ago, it was totally different. When I was a kid, very different. And we'll talk about that in a little bit. Okay, so here we have our numbers. We have 21, 15, 13, 17. I am going to put those and just get some statistics out of it. So I'm going to go to the one variable statistics calculator, which we've used a lot already. Might even be the most important calculator. Has it gotten older or younger? It's gotten a lot older. I'm telling you, my childhood time, we had so much more fun than you all had. Just to let you know that. Okay, now I'm not going to get involved in anything else because it gets a little rude, I guess, but you get the idea. Okay, this is a sample. It's a sample of our class, okay, or a sample of students. You can look at it this way, current students, and then hit calculate. Okay, the mean of 16.5, that the symbol we use is X bar. Remember we talked about the mean, and this is a sample, so it's a sample mean of 16.5. So I'm going to go down here and I'm going to pop in these numbers here so we can look at them again. 16.5, okay? The standard deviation was 3.4157, about 3.4 or so. N was 4. Okay, so far, any questions on getting these numbers? How do we get the standard error? This one's actually one of the easier ones. Good thing we have a sample size of 4, it makes it easier. So how do we get the standard error? Do you remember that was last week? We had a formula for it. So we're kind of reviewing last week's. So what is it? How do you get the standard error if we know X bar is 16.5, S is 3.4157, and N is 4? And if you want, maybe I'll go 1 decimal place instead of 3. That's good enough for me. The standard error is not the same as S. Okay, it's not the same as S. It was a formula. It was part of the central limit theorem that said the standard error is the standard deviation over the square root of the sample size. So the first thing is, it turns out that I'm not even going to put an equal here. Well, let me do it. Nope, that way. So new equation. There we go. I'm going to put approximately equal. That's that little wavy equal. Because we don't know the exact sigma, and we never will, by the way, because you'd have to ask everyone. So you don't know the exact segment. We're going to get into that, why that's important and what we have to do because of that. So that's going to be S over the square root of N, which is 3.4 divided by, actually, let's write it, since I'm in the equation, I can do it nicely. There we go. So 3.4 divided by the square root of 4, because that's our sample size. And one wonderful thing about this is the square root of 4 is a nice number. Usually I don't get so lucky when I go over this. I told you I've been doing this for decades. Usually it's not just square root of 4. Square root of 4 is 2. 3.4 over 2, you can put in your calculator, but I know it's 1.7. Any questions on that? So that gives me an idea of how far from my sample mean the population mean is likely to be. That's what the standard error gives you. Does that make sense? Any questions on that? Because that's a really important concept. Okay, if I wanted to decrease my standard error, let's say by a factor of 3, how big a sample size would I need? Instead of a sample size of 4, what do I need? It turns out not 12, because the square root of 3 doesn't help. You need to multiply by 9. You need 36, because the square root of 9 is 3. Do you see how that works? Okay, so if you want to decrease the standard error by a factor of 3, you would have to have a sample size 9 times larger. Any questions on that? That's really important to understand that concept. It's not that hard math, but you have to remember to square it when you want to see what the factor you need, because you're dividing by the square root. Okay, now I'm going to show you a little picture. This is how things work. So, by the way, can we say we have a normal distribution? Absolutely not. How come? In terms of sampling distribution. Yeah, it's less than 31. Okay, less than 31. So, right, it's not greater than 30 is another way. So our sample size is too small. We don't have a normal distribution. I just want to let you know this is a terrible example because our sample size is too small, but I think you understand why I couldn't get a sample size of over 30 today. Because we don't even have that many in our class, even if everyone showed up. Okay. So we're going to pretend that we have a normal distribution to start with, and then you can do it. Okay. But there's some issues. Okay. So one thing is what we can do is we can say X bar. We can consider that the center because X bar, if you remember, is our best guess for the population mean. So that means we can put X bar in the center of this normal curve. Does that make sense to everyone? And then what we can do is we can say, well, we want to find, let's say, a 95% confidence interval. So what we want to do is we want to say, how far left and right can I go so that this is symmetric and the area under the curve is 0.95. Any questions on that? Okay, and by the way, sometimes you say the area under the curve is 0.95. You could take 1 minus that. That would be 0.05 or 5%. Divide by 2, and those are the outer sides. And those are often called alpha over 2s. That's going to come up next week. So just give you a heads up. So this is the big picture. This E is called the margin of error, often just called the error, because the idea is we can be 95% confident that the population mean is within that range because there's a 95% probability of it being in that range in a way. Have I lost anyone of this idea? And it's all part of the central limit theorem because we have a normal distribution and we want to be 95% confident, which means that we want to make sure there's a 95% probability. And I'll get into more wording in a little bit, but for now, we're going to keep it there. Any questions on the wording? Okay, so then, and you're used to this, what do you think, how do you think we're going to find this lower bound and this upper bound? Any guess? Here's the hint. The math would be really hard if you had to do it on hand. Yeah, it's time to grab the calculator. Okay. If you want to truly learn, you need to become, by the way, being a math major is not enough. You need a master's or a PhD in math, just to give you an idea. If you want to get all the math down, it's brutal. But we're not going to. We're going to go back to the calculator menu. And then what calculator do you think I want to use? What number do you think? So you're saying 9 or 10. So the question is, did we get data from the survey or did we get statistics? What was the original thing given? Data, right? I asked you and the original was data. So this is one of those data, and data is the most common, by the way. But statistics can happen. If you're only given statistics, you go to the statistics. So we have our data. And I think, yeah. No, that wasn't it. All right, let me recopy and paste the data in. Oh, sorry. No, I got the wrong one. Thanks. Back to the calculator menu. I clicked the wrong one. Confidence interval for me with data. I would have found that out right away as soon as I looked down. And then go 21, 15, 13, 17. So just remember, you got to put commas between every number. And also, if you ever have a number like 10,500, don't write 10, comma 500. Don't ever put commas in for large numbers because you're used to it. Is that clear? Don't make that mistake. Okay, CL stands for confidence level. And here the confidence level is 0.95. Any questions on that? Any questions? And then hit calculate. Okay, and something, so you could look at this. We have X bar and we have S. So I put those in because those are important. That way you wouldn't, even from the beginning, you wouldn't have had to go to the first calculator. You still get X bar and S. But the important thing is we have our lower bound and the upper bound. Do we need all these decimals? What do you think? Do you think anybody would ever care? Yeah, no one cares about 1/1000th of a year on how old you are on the average, right? I've never met anyone that cares about that. Okay, so maybe maybe 1 or 2 decimals is all you would need. Does that make sense? Okay, so maybe I'll go 1 decimal. That's probably enough. You might care about whether you're 11 or 11 and a half years old. Does that make sense? But you don't care if you're, 11.06493823, all that stuff. So I'm going to go to just 1 decimal. When you're doing the online assignments that are computer graded, whatever it tells you to do, make sure you do. If it says 4 decimal place, round to 4 decimal places. Is that clear? Because that's a common is 4 decimal places. But I'm going to make it easy to read. 1 decimal place would be 11.1 to 21.9. So let me just put this in. And I want to mention something else. This is something that, again, we all have our things that we do when we're on vacation. One of the things I did when I was on vacation is I added coding and I added stuff to this program. But what I added was a picture. Can you see the 95% confidence interval? So this area is 0.95, and it goes 11.1 to 21.9. Any questions at all on that? And the sample mean is 16.5 because that's our best guess for the population mean. Okay, so if our best guess for the population mean is 16.5, does it mean it's 16.5? Does that mean that's what the population mean is? Yeah, definitely does not mean that. It does not mean that that is the population mean. It's just our best guess. But now we have not just a best guess, but now we have a range of values that we can be confident that the true population mean lies between. Okay, unfortunately, our range is really wide. Yeah, it's somewhere between 11.1 and 21.9. Okay, but it doesn't mean it is between those numbers. This is a 95% confidence of it being between those numbers. Do you see how that works? So now, once we've got that, I want to mention one more thing, and that is up here. Right here, I said that standard error is not exactly 3.4 over root 4, but it's approximately 3.4 over root 4. Why was it approximately 3.4 over root 4? You remember? Yeah, we don't have sigma, we only have S. So it turns out there's an extra error involved in not having sigma. Even if we had a large sample size, we still don't have exactly sigma. We still only have S. And we'll never get, pretty much almost never get sigma. Does that make sense? It turns out that if you have a large sample size, then that error that you have because you're using S instead of sigma is much smaller, but it's not zero. So it turns out it's kind of a fun, one of my favorite stories is that there was a guy and he realized that when he was doing the studies and he was using the standard error with an equal sign basically, and using the normal distribution, that he wasn't getting the population mean 95% of the time, because that's what you should get, right? So it means you have a 95% probability of being right. And he wasn't. Any questions on that idea? And you would never guess what I'm about to say. It was all about beer. Anyone know why? Okay, because the person who did it worked for a brewery and was doing statistics for this brewery. Isn't that cool? And he realized that the statistics he was using wasn't quite right. And he came up with a new distribution that's not exactly normal, but not that far from being normal, that kind of put in that extra error for not knowing the population standard deviation. And I actually learned something, what I'm about to tell you, 2 days ago when I was watching a Harvard, I think upper division statistics course or probability statistics course, and about the history of this thing. Because he worked for the brewery, and he did not want anyone to know that he was working for the brewery and doing statistics for them. So he he didn't name it after himself. He just said student. And it's called the student's t-distribution. And the student's t-distribution is a distribution you're going to use when you don't know the population standard deviation, which is most of the time. Okay, so that is this extra. It's called the student's t-distribution. If you have a large sample size, you wouldn't even notice the difference between the student's t-distribution and the normal distribution. Slightly different. If you have a small sample size, it becomes more obvious. Okay, so now what I want to do is I want to interpret this confidence interval. So let me type it out. So with, you always must start with the word with. 95% confidence. We can conclude that the population mean age of first passionate kiss is between, and now we look at our numbers, 11.1 and 21.9 years old. Okay. Yeah, almost turned lethal. Yeah. I'm not the perfect typist, but I'm good at fixing. Okay. So I want to note that you need to get used to writing this out. Okay. I'm going to ask you to interpret the confidence interval, and it's going to look real similar to this every time. It won't always be about population. It won't always be about passionate kiss. Who knows? It could be about something else, whatever you happen to be studying. Okay. It obviously won't be always 11.1 and 21.9, but that's what we got. Okay. But the word with will always be there. The word confidence will always be there. We can conclude that the population will always be there also. Okay. And if you're talking about the mean, it'll be population mean. Okay. So then the question is, what does it mean to be 95% confident? And let me give you a little history. This was about let's see, what about the sample? I'm not sure what you mean by what about the sample. What we're interested in is a population mean. So that's what we're confident about. The sample mean, we were 100% confident of the sample mean. There's a sample mean. We got it. Okay. Yeah, so I want to make sure you watch the I want to make sure you watch the webinar. So, pay attention. It allows me to force you to watch the webinars, which I know you all are doing, but not everyone does that. So about almost 100 years ago, any of you know who was in charge of news 100 years ago? What company? It's history, it's not math. No, New York Times. Okay, there was no television, by the way. That was the New York Times, and they were like literally in charge of news. And the idea is if you are a news agency, okay, or a researcher, then you can think that you're going to be doing this a lot. Does that make sense? You're going to be collecting samples and coming up with confidence intervals. So this 95% is the percent of the confidence intervals that you could collect that will be correct in that will actually capture the population mean. The other 5%, those are the ones that you screwed up on. Okay, it doesn't mean anything wrong, but you got really bad luck and you ended up with an interval that doesn't contain the population mean. Does that make sense? So the way we can word this is the following. If many samples of sample size four, because remember we used our n was 4, are taken, then each one will result in a different confidence interval. If I ask 4 different people, how old were they when they got the first kiss? You're going to get different answers and you get a different confidence interval. Does that make sense? 95% of these confidence intervals will contain the true population mean age of first kiss, of first passionate kiss. The other 5% will not contain the population mean age of first passionate kiss. All right, so the New York Times decided that 95% should be the standard for news. And whether you like it or not, that's what they decided, and people agreed on it. It had to actually do with another news agency that got the presidential election wrong. But I'm not going to get into all the history. I don't remember the president it was, but and people trusted the New York Times, and the New York Times uses that 95%. Okay, does that mean you always should use a 95% for everything you ever would do? What do you think? So if you take the mode, it should be correct. We're not talking about the mode here. This is average. This is a mean. Yeah, so I'm not sure what you mean by if you take the mode. There's nothing with mode here. And in fact, with these 4 numbers, there was no mode. Everyone had a different number. Yeah, so the idea is it depends on the scenario. When do you think you might want to be a lot more than 95% confident? In what kind of situation? Not with this particular example, but who might not be okay being wrong 5% of the time? The model of the mean, the mode of the mean, still not quite understanding. Who might be not okay with 5% of the time being right? Yeah, doctors. Politicians are fine with it. Doctors, yeah, if there's a 5% chance that based on your results you're going to kill someone, and maybe all you're doing is doing some procedure to, I don't know, clean up acne or something, that's not okay. I hope you all agree with that. So there are times when 95% confidence is not okay. Okay. There's also times when 90% confidence is fine. But, and I want you to understand this, why not just use 99% confident instead of 95? 95 if you can be more confident. Why not be more confident? It's not that it's harder. And this is where, remember I told you I was going to wait? Let's turn this into 99%. I can do it with the same sample size. I'm going to do it with the same sample. I can make that 99. And I calculate, and look what happened to the upper and lower bounds. Now they're between 6.5 and 26.5, which is totally useless. Does that make sense? I mean, of course, the average age of first kiss is going to be older than 6.5 years old for a passionate kiss, by the way. Now, 7-year-old children do not have passionate kisses. They don't have those hormones yet. Okay? And it's not going to be over 26.5 either. Okay? That's not what our society is. Does that make sense? So if you want to make a more confidence, you could do that. And by doing that, it's kind of a give and take. You get better confidence, which sounds good, but you get a wider margin of error. On the other hand, if I want 0.9, 90%, and I hit calculate, now I have a smaller margin of error, 12.5 to 20.5. So what's good is we got a smaller margin of error. The problem is now there's a 10% chance that we're wrong. So there's a bigger chance of being wrong. Do you see how that works? What's the only way to get a larger confidence level and a smaller margin of error? Yeah, larger sample. Yeah, we need a larger sample. Because if you have a larger sample, that's going to make things better. And then you can have a large confidence level and not have this giant margin of error. And in fact, our sample size was 4, and we have, even with 90%, this is really wide. This doesn't tell me anything. Does that make sense? Okay. The funny thing is, every one of my friends and people I hung out with when I was a little kid, they all had their first kiss before 12.5 years old. I was 13, and everyone laughed at me because I was so old, just to give you an idea. Society was different in the old days. Okay, but I did finally kiss someone at 13, and that was like super old. But nowadays it's different. Okay, and again, statistics, you can actually see it happen. Okay, any questions at all on this give and take between the confidence level and the margin of error? So again, the only way to make both better is to get a bigger sample size, because a bigger sample size makes your standard error smaller. And if your standard error is smaller, your margin of error is smaller. And then you can make your confidence level a little bigger, and it'll be a little bit bigger. But if you have a really large sample size, you're good. Do you see how that works? In the project, you're going to have to analyze, and you're going to have to decide how big a sample you would need if you wanted a 99% confidence level. Do you see? With the same margin of error, that kind of thing. Those are the kind of things you're going to have to be able to do. Any questions on this example? Okay, just a note, and remember this is recorded, so you can write it out, but you don't have to. I have a template for the conclusion, and that's with whatever confidence. It can be concluded that the population mean, whatever you're talking about, is between those two values, something and something. XXX means don't write XXX in your answer. It means fill it in with stuff. Does that make sense? And for the interpret the confidence level template, if many samples of however many sample size are taken, then each would produce its own confidence interval. Whatever percent of these confidence intervals will contain the true population mean of whatever you're talking about. And 1 minus that percent, or 100% minus that percent, won't contain the true population mean of whatever you're talking about. So I have a template so that you can use that. And then you can get the problems right. And again, if you pay attention, you'll get, at least high partial credit if you get that part right. And there's a good chance you'll get 100% if you get that part right. And that you'll need for pretty much everything that's happening this week. Okay, so that's going to be the exam and the discussion assignment. You'll need those. Okay, and then you still need a sample size over 30. Otherwise, none of this calculation works. Unless you happen to know the population distribution is normal, which you almost never do. Okay, so then you have to assume it, which is usually wrong. What is the first one? Do you mean the first template, the conclusion template? Does that mean by what is first? Yeah. So here it is. With whatever confidence, it can be concluded that the population mean blank is between blank and blank. Okay. And by the way, in a bit, very short time, we're going to be walking away from means. Any guess what we're going to move into? Thinking about last week? And what I've already said in terms of our agenda today? Remember? Distributions, not quite. Proportions, there we go, proportions. So here is, the thing I love about this class is that I can go grab the news any day and find something about what we're doing. So here's the question I have. What percent of Americans feel that inflation will affect their Valentine's Day plans? Okay. Hopefully you're all aware. Maybe you're not. When is Valentine's Day? Maybe you're not aware. Yeah, in a couple days. Yeah, February 14th. So in a couple days is Valentine's Day. So in the news was this question. And it was by The Hill. And they did a study. Okay, so of course, there's no way in the world they can find out the exact percent of all Americans. And maybe I'll write adults. 1-year-olds don't care about Valentine's Day. So I'm going to go for adult Americans because obviously that's who they surveyed. Okay. So they did a study. They did a survey. That's all you can do. You can't ask everyone. And I know they didn't because they didn't ask me. I never had anyone in my class get asked when I give an example. And if you get asked by The Hill, I'm sure it's a no. But what we want now is not exactly what percent, but what is our best estimate and what's our confidence level. Does that make sense? Our confidence interval, sorry. So based on the article that I read and kind of put in here, they surveyed 200 people. Is 200 a lot, by the way, or a few? What do you think? Okay, it's a lot over 30, isn't it? Okay, but here's something to note. When you are doing the yes/no survey question, 30 has nothing to do with what's a lot and what's a little. Okay, we're going to see in a bit Typically what you want is 1,000. They're actually on the low side. Okay, when you have the yes, no question. But what they had, again, in the article, which I read, was that p hat was 0.46. So they cited that 46% of the people that they surveyed feel that inflation will affect their Valentine's Day plan. Yeah, it does have to be 6 or more to use the normal distribution, but it turns out you need a whole lot more than that to have a good interval. Okay. All right. So how do we get the number of yes answers? We want that to be greater than 5. Remember how to do that? Yeah, we take NP. NP is 0. It's 200 equals 200 times 0.46. And that one, I could do that one in my head, actually. That's 92. Always welcome to use a calculator. And 92 is it greater than 5? Yes. Okay, so I could take the question mark out because it's a yes. And then the number of no answers. There's two choices. You could do NQ or you could do 200. Let's go like, let me. No, won't let me. So let's do this. So the number of no's will be 200 minus 92, which is 108. And that is also greater than 5. So that means I can actually do the calculation using the normal distribution. Otherwise, you can't. Otherwise, turns out we won't ever do this in this class, but if you don't have a big enough sample size, you can still do it using a binomial distribution, but I'm just not going there. Sound good? And you won't ever have to in this class for the confidence intervals. Okay. So now I want the confidence interval. So will this calculator work? It will not work. This calculator is for means. This won't work. It wants a bunch of numbers. We don't have a bunch of numbers. So I go back to the calculator menu. Which confidence interval, what calculator number do I need? Yeah, number 12. It's actually not for with statistics. It's just for proportions. So N was 200. X was 92. Any questions on that? Because that was the number of yes answers. What do you think you should use for a confidence level here? Yeah, never 95, but 0.95. Okay. And I put in the instructions here, if you want 95%, enter 0.95. The 0 doesn't matter, but can't hurt to write 0. Just easier to read. And hey, calculate. Any questions? Any questions? I tried to make it easy. Again, in the old days, when I first did this was so brutal. But we don't do that anymore. Now we can just use a calculator. Okay, did that look pretty easy? Hopefully it did. Okay. And I'm going to go to the 2 decimal places, 0.39 to 0.53. Any questions on that? That's a pretty widespread. As I said, the sample actually is pretty small. 200 is not that big. Because to say we're between 39% and 53%, that's pretty wide. Does that make sense? Okay. Just a note, by the way, if you take, this is kind of important, so let me mention this. Margin of error. That is going to be 0.53 minus 0.46, which is equal to 0.0, let's see, 47. That's called the margin of error because our best guess was 46%, right? That was our best guess for the percent of all adult Americans that feel inflation will affect their Valentine's Day plans. This 7% or 0.07, that is kind of the idea of how far off we might be up to point. So another way of saying is we're 95% confident that our best guess of 0.46 is off by no more than 7%. Does that make sense? Anyone lost on that idea for margin of error? Okay. If you're not given this 0.46, you can always just add these up and divide by 2 and get the 0.46. Because the center of the confidence interval will always be your population proportion or population mean if we're doing means. Any questions on that idea? Okay, let's interpret the confidence interval. Okay, with 95% confidence, we can conclude that the population, but do not write population mean, population proportion of all adult Americans that feel inflation will affect their Valentine's Day plans is between 0.39 and 0.53. Another way of stating it that's sometimes a little easier to understand is I can copy and paste this part with 95% confidence. We can conclude that between 39% and 53% of all adult Americans feel inflation. Let me just copy and paste. Will affect their Valentine's Day plans. I want to do the following. I want to let you know that that word all is very important. If you don't put the word all in, what's going to happen to you? Yeah, you're going to lose, no, you won't lose all of your points, but you can lose some of your points. I won't give you a 0 on the exam because you didn't put the word all, but I'll take a point or 2 off. So, it's not hard. It's 3 letters to type, so do it. Got it? Yeah, so make sure that you emphasize. By the way, that's this week, next week, and the week after. It's all going to be about the population. Notice population. Do not talk about the sample proportion. You're talking about the population proportion. Got it? Okay, let's interpret the confidence level. Okay, that is that if many samples, or how about groups is probably better, of 200 adult Americans are surveyed, then each group will result in its own confidence interval. 95% of these confidence intervals will contain the true population, and don't write mean, proportion of all adult Americans. And I think at this point, I'm just going to copy and paste that fuel inflation will affect their Valentine's Day plans. Any questions at all on this confidence interval? Notice the first part is interpret the confidence interval. The second is interpret the confidence level. So make sure you answer the question right. Read the question, okay? Interval is not the same thing as level. Sometimes I could also say, what does it mean to be 95% confident? And that's the same thing as interpret the confidence level. You know, sometimes you say that 95% represents a probability. What does that probability mean? And that's what this means. Any questions at all? Any questions at all on that? Which interpretation must you use? Well, very important if you look at the first one or the second one. Oh, you mean of these two interpretations? Either would work. They're both correct. Second one's a little shorter in this case. A little less typing. If those are the two you're looking at. So as English, there's a lot of ways of saying things. That's why I gave you two different ways. They say the same thing. Yeah, so it all depends on, what side of the bed you woke up that morning in terms of which one makes most sense. Just let you know. They really say exactly the same thing. All right, so now we're going to get into a sample size for the mean. Okay, so the idea, and this is really important, let's suppose we want to conduct a study and we want our margin of error to be no more than a certain amount. And let's suppose we want like a 95% confidence level. Okay, if we have an estimate for sigma, then we can actually find out how many people we need to survey. So here's the math. So we know from the central limit theorem that sigma sub x bar equals sigma over root n. Do you remember that from last week? Any questions on that? Okay, so it turns out that the margin of error, we go back up, far up here, that's the distance from this x bar to the x bar plus e. Okay, well, that distance is basically proportional to sigma sub x bar. And that proportionality constant has to do with the z-score. Okay, it has to do with how many standard deviations you're okay being away from it. Has something to do with that. So the math is that E is equal to Z times sigma sub x bar, which is equal to Z sigma over N. Okay. Now I can solve, and again, you can trust me or you can do the algebra yourself, and you get n equals z sigma over E quantity squared. And that is the formula for calculating the sample size needed for the mean. Any questions on that idea? Okay. By the way, how might you come up with a sigma? Any thoughts? Yeah, you do what's called a preliminary estimate or a preliminary study, and that even can be a small sample size. You could do a sample size of 10 or something, and you can do the standard deviation of that sample size, and you can use that as your estimate for sigma, as your best guess. Because you never know exactly the sigma, but you can get a guess by doing a small sample size and using that as your guess. The other way of doing it is you say, well, sigma covers kind of the little, 68% or so of the data. So you can kind of look at, your kind of normal range that you might have, and then divide by 2, sorry, because you're on both sides. That's another way of getting it, of sigma. But usually in this class, you'll just be told. Just let you know that. Okay. Z is a Z that corresponds to your confidence level. So it turns out, and that comes from the empirical rule. So it turns out that, if you have a 95%, remember that was 2 standard deviations away. A little more accurate than 2 is 1.96, it turns out. And if you want to be 1 standard deviation away, that's 1.645, it turns out. Okay. So there's all kinds of, numbers like that. But I'm going to show you an easier way. Okay, so here's an example. Suppose you want to find a 95% confidence interval for the population mean hourly wages of nurses in California. Based on a preliminary study, the standard deviation is assumed to be $25 an hour. Okay, that's kind of a guess. If you want a margin of error to be no more than 50 cents, how many nurses must you survey? Any questions on the question? I want to highlight how many nurses must you survey. Those words tell you that we're asking for the sample size. We're not asking for a confidence interval. Because if you are confused about what's asking for, oh boy, you're going to get them wrong. So it's really important to look for the keywords, see what it's asking for, and this is what is a sample size. So, back to the calculator menu. Any guess on what calculator I might need? Which number? Yeah, this is 11, sample size for a mean. Okay, I want to give you a heads up. When I made this calculator and posted it, there were some faculty, not at my college, but some other colleges that got mad at me. You know why? Not because it's wrong, by the way. There are no errors. Okay. No, that is a sigma, actually. No, they got mad at me because it's too easy. And they wanted the students to do the algebra. Okay, so just let you know. So sigma was what? Based on this example, what was sigma? Yeah, sigma is 25. That's our standard deviation. So it's important to understand these symbols. Sigma is standard deviation, that's 25. E, what's E? Based on the question? Yeah, that's the 0.50. because that's your margin of error. By the way, the original textbook written by Barbara Lasky and Susan Dean, they have just confusing language for this E. They had all these different letters depending on what situation you're in. I hated it. So actually, the good thing about this whole open educational resource stuff, not only is it free for you all, but I actually have the ability to change things. So I just call it E. So I changed the book. Okay, so to let you know that I made that happen. And a lot of people liked it, so that's good. I even talked to Barbara Lasky, and she was like, yeah, that makes sense. Okay, and then CL. What's CL? Yeah, 0.95. And hit calculate N. I want to let you know something. Part of the way this calculator works is it rounds up. So if you actually did the algebra calculation, you might get 9,603.1. But the thing is, if you round down to 9,603, then you're going to be just a little bit too small. And the question is, you want to make sure that you have it no more than that margin of error instead of a little bit more. You see? So you would have to survey 9,604 people. That's a lot, by the way. And sometimes you got to do a lot. If you wanted to do fewer, what could you change with this example? You know, if this was really your study, what could you change? If that was just too many people to survey. Yeah, so 1 is a percentage of confidence. So instead of 95%, what percent could we change and then have fewer? Any guess? Would you change it to the 99 or the 90? Yeah, the 90. The 99 would make it more people. And you can just do that. That's the good news, is with this calculator, you just type it in. It changed pretty much, didn't it? Now it's only 6,764. That still may be way too much. So the other thing you can change is the margin of error. So if you were okay with being $1 off instead of 50 cents off, make the margin of error 1. Now it's looking a lot better. Do you see? Still a lot of work, but it's a lot less. I do want you to understand how things are going to change, not necessarily formula-wise, but if the margin of error goes up, then the sample size goes down that's needed. Do you see that? If the confidence level goes down, then the sample size needed goes down. So I do want you to understand those pieces. Any questions on using the sample size calculator when you're talking about means? Okay, so again, if you don't have a sigma, you can't do it. Okay, you always have to get a guess for a sigma. And you often, that's either from just what makes sense, you know, what do you think it might be off by, or by doing a preliminary study. Let's do another example. And for this one, I didn't even put in the math. We're just gonna have a question. So suppose you want to find a 99% confidence interval for the population and proportion of cars in the United States that are electric vehicles. Might be a fun thing to do, right? Okay. If you want a margin of error of no more than 3%, how many cars must you look at? Any questions on the question? Okay. Will this calculator work? Why not? Why will this not work? It's not about we don't have sigma. This is for means. This is not for proportions, and they're completely different. The math is 100, like really different. So calculators just can't, like, just, oh, you meant proportion, so now I'll figure it out. No, it's not even close to the same. So I need to go back to the calculator menu and tell me what calculator number I need. No, 11 won't work. That's for means. 13, because we have proportions, right? If we go to the survey question, it's, is your car an electric vehicle? And the answer is yes or no. These are proportions, not means. Very important. Pretty much for everything we do for the rest of this entire course. That should be the first question you should ask is, are we talking about a survey question that's yes, no? Or are we talking about a survey question that is quantitative with a number answer? Does that make sense? Very important that you have that down, or it'll just go really bad for you for everything we do for the rest of this entire class. Okay, there'll be other things you have to ask too, but that's usually the first one. Okay, so now do we have an estimate based on that first question? Do we have an estimate for the proportion or do we not? Let me read it again. You want a margin of error no more than 3%. We want to be 99% confident. Do we have an estimate? We do not. So that means make sure this no estimate for P is chosen. Our margin of error is 3%. Should I type in 3? What do you think? No, what should I type in? Yeah, 0.03. 3%. Turn it into a decimal. Confidence level, we wanted a 99% confidence level. So that's 0.99. And hit calculate in. 1844. Any questions? Any questions? All right. The second question, if you look at last year's data, okay, I actually went online and looked. 2.2% of all cars are electric vehicles. How many cars would you need to look at for a 99% confidence interval now? Okay, so you had a question, confidence level or confidence interval? The calculator's confidence level, CL, or confidence level, but it's interval for this question. Okay, so the calculator actually has both because it's hidden. CL is confidence level, N is a sample size needed for a confidence interval. Does that make sense? So the confidence level is a component of the confidence interval. Yeah, they go together in a package. They're not separate. They're different things, but they go together. You can't even talk about a confidence interval without having a confidence level, because you have to start with whatever percent confidence. That's your confidence level. And then you talk about the interval. And the question is, what we're doing is how big a sample size do you need to make that happen? All right. So now we have an estimate for P. So I click have an estimate for P. Notice now it gives us an extra box, estimate for P. What's our estimate for P? Yeah, 2.2%. If you move the decimal over 2 places, 0.022. We're using the same margin of error, same confidence level. Now I hit calculate. Did things change, by the way? A little or a lot? Yeah, a lot. Now we only need 159 cards to look at. So the answer to this one is 159. Oops. So we need to look at 159 cars. Notice it's a huge difference. And that has something to do with the fact that it's actually a very small percent. It turns out that this, again, I'm hiding the math, but it turns out that if you don't have an estimate, turns out you're using 50% as your estimate. And I'm not going to get into the mathematics, but you can trust me. And there's reasons behind it. Any questions at all on this example? Okay. I do want to let you know that today is, a bit lighter because it's too early to get into anything fancy. Also, you have an exam. So we're going to finish a little earlier today, probably. I'm going to say one thing after. We're going to show you something. The secret word is with. Why did I use a secret word? Why did I use with as a secret word? Anyone know? Yeah, if you look at the confidence interval stuff, first word of the conclusion template is with whatever confidence. That's how you start. And sometimes starting is important. If you don't know how to start, you just get stuck and lost and start crying. But if you remember that one word, that can get you going. Does that make sense? So that's a secret word. I want to mention something. It's actually a little bit early to do any planning on this, but I want to mention a few things, and that is project 2. So close to half of project 2. Any guess on what it's going to be about? Yeah, not another one. There's 2. I used to have 3, and it was just too much for students. Now it's only 2. Any guess on what project 2 is going to be a big part of? Project 2 will be? The hope is you could guess it. Don't see everyone jumping in. Yeah, confidence intervals. I'm not gonna say these confidence intervals, but confidence intervals. So we're not quite ready yet because it turns out project 2 is you need chapter 10, and we're in chapter 8 right now. Because it's going to be a comparison of 2 different things, and we don't know how to do that with confidence intervals. And we're also going to be doing hypothesis testing, but I want to give you a heads up that you're going to have to be, really getting into confidence intervals. So today is day 1 of understanding a big part of the concepts that you're gonna have to know in project 2. I want to mention something else. You are allowed to use the same partners if you want to that you used for project 1. You are also allowed to change partners. What you're not allowed to do is go by yourself. You're not allowed to submit the project without a partner. It's the same major deduction. It's almost impossible to pass if you don't have a partner. I think it's like 25 or 30% deduction. It's like big deduction. So make sure that you have partners. Make sure your partners don't drop. If they do, you need to find more partners. If you didn't have a partner, get partner. Okay. You have a lot of time. There's still a lot of weeks left before the project's due. It's due like towards the end of this course. Don't wait until towards the end of the course to find partners. Big, big caution. Even though they're not ready to even start the project, you're at least ready to make sure that your partners are okay working with you. And if not, find partners. Does that make sense? Also, something I didn't do and I probably should. If I go to discussion, I am going to get rid of the project 1 discussion forum. I'm going to get rid of it in the pinned discussion. And I'm going to put project 2 discussion forum. And I'm going to pin that one. So if you're going to look for a partner for your project, because maybe you didn't get along or dropped or whatever it might be, then post in the project 2 discussion forum, I want a partner. Does it make sense? Any questions on that idea? Okay, there's nothing fancy about this forum, just like the other one. Just you post, and that's it. There's nothing in it yet. But if you post, there'll be something in it. So that is something that's really important, is make sure that you have partners. 3 is better than 2. 1 is not okay. And I've just started grading the project. It turns out I had to substitute for the calculus class. So I've been teaching almost all day long with like hardly any break. So I was able to actually do one. Haven't done a lot, but there's going to be a bunch more. Tomorrow I'll do a bunch more. Definitely by Thursday I'll be done with the projects, but it takes a while to read them. I might be done tomorrow, but Thursday is for sure. I'm not a procrastinator, but it takes a long time, many hours. So, and I put a note in my I put something in my notes that says that it either says ask your partner, whoever it is, to share my comments, or if you're the one I commented to, then it says share with your partners. Okay, with the names. Okay, so it's really important to share my comments with your partners if you're the one that got the comments on the paper itself. Does that make sense? Because your partners can't see the comments I put on your paper if you're the ones I put it on. That's why you gotta, chat with them. Okay, and I do put a lot of comments on. Any questions at all about any of this stuff? Okay, I think, again, it's a little shorter than usual, but you do have an exam this week. And again, we're not talking about the next project. That'll be in 2 weeks, by the way. Then we talk about the next project in a deep way. Okay, a little bit more next week. Next week, we're going to be doing hypothesis testing, which is really important. Pretty much next week and every week after that, we do hypothesis testing. So that's a biggie, biggie, biggie. So make sure you pay attention. Okay, confidence intervals are important too, but hypothesis tests are number 1. So I am going to stop the recording.